All right, welcome, future captains. Today, we're going to move way beyond the textbook. This is your masterclass on the float-type carburetor. Now, I don't want you to just memorize parts. We are going to build this system from the ground up, from first principles. Then, we're going to break it, and we're going to fix it piece by piece. This is the kind of deep understanding that separates a pilot from a captain.
Look, when you're in that final interview and the examiner leans across the table and asks you to explain a system, they're not looking for a definition they can read in a book. They're testing your foundational knowledge. They want to see if you can think like an engineer and, more importantly, act like a captain. So let's get you ready for that question.
So we're going to start by building the most basic carburetor imaginable. And what you're going to see is that its entire operation, the whole thing, it hinges on just two fundamental laws of physics. If you can truly understand these two principles, every other component we add on is just a clever solution to a very specific problem. Okay, here it is. This is our starting point, the simple float chamber carburetor. Let's just walk through the key players here. First, you've got the float chamber, which is basically our fuel tank that keeps the fuel at a constant level. Then, the heart of the whole system, the venturi. That's what's going to turn simple airflow into a pressure difference. The main jet, that little calibrated hole, that's what meters our fuel. And of course, the pilot's main input, the throttle valve. So, principle number one, the U-tube principle. You see, the float chamber's job is to keep a constant fuel level, always just a little bit below the discharge nozzle. This creates a really stable, consistent pressure head. Now, why is that so important? Well, it ensures that the pressure pushing down on the fuel is always the same, which makes precise fuel metering possible. Without that constant reference pressure, the whole system would just be wildly unreliable. And second, and this is the magic trick, the Venturi principle. As the engine sucks air through that narrow throat, the air has to speed up. And Bernoulli's theorem tells us that as the velocity of a fluid goes up, its static pressure must go down. So the pressure inside that Venturi throat drops below the atmospheric pressure that's sitting on top of the fuel in the float chamber. And that pressure difference, that is the engine of the carburetor. It's the force that literally sucks the fuel out into the airstream. So the whole process is pretty straightforward, right? Air speeds up, pressure drops, fuel gets pulled out, and it atomizes into the airflow. And you know what? It's a functional system, as long as you're at one fixed altitude. But an aircraft, by its very definition, climbs and descends. And this simple design has absolutely no way to account for the changes in air density. And that right there is its critical flaw. Okay, so let's introduce our first real-world challenge. An aircraft doesn't just sit at sea level. We need a system that can actually adapt to the changing density of the air as we climb up and come back down. So think about it. As we climb, the air gets less dense. The engine is still pulling in the same volume of air with every stroke, but the actual mass of that air is decreasing. The problem is our simple carburetor only cares about volume, so it keeps metering the same mass of fuel. And what's the result? The mixture gets richer and richer and richer, to a point where it becomes dangerously rich. So the solution comes in two flavors. Over on the left, you see the automatic fix, the pressure balance duct. What this does is it makes sure the float chamber is sensing the pressure right at the air intake before the venturi. So as ambient air pressure drops with altitude, the pressure in the float chamber drops right along with it. It's a really passive, elegant solution. And on the right, well, that's the pilot's direct command, the mixture control lever. It's basically just a needle valve that lets the pilot manually restrict the fuel flow, giving you precise control over that mixture.
All right, let's tackle the next challenge. An engine doesn't just run at one speed, does it? We need to deliver the right fuel-air mixture all the way from a slow idle on the ground to full takeoff power. And our simple main jet just can't handle that entire range all by itself. Okay, so picture the engine at idle. The throttle valve is almost completely closed. That means the airflow through the main venturi is just a trickle. It's not nearly enough to draw any fuel from that main jet. The main circuit is effectively off. But the engine's pistons are still trying to suck air in, which creates a really powerful low-pressure area, a big depression, right behind that closed throttle plate. The slow-running jet is perfectly positioned to take advantage of this, and it provides a separate, rich mixture to keep the engine ticking over nicely at low RPM. Now, what about the other end of the power range? As the engine speeds up and airflow increases, a simple jet naturally tends to deliver a mixture that gets progressively too rich. The air bleed diffuser is the brilliant solution to this. See those little holes in the diffuser tube? As the fuel demand goes up, air gets sucked in through those holes, and it creates an emulsion. Think of it as a frothy mix of air and fuel.
This emulsion not only flows more easily and atomizes better, but critically, those air bubbles also take up space, restricting the fuel flow just enough to lean the mixture back to the correct ratio at higher power settings. It's really clever. And finally, we have to deal with the dynamic changes. The pilot jamming the throttle forward for takeoff or demanding maximum power, which, as you know, requires a richer mixture for engine cooling. So what happens when the throttle is snapped open? Well, the air is light, it's a gas. It responds instantly. But the fuel, it's a heavier liquid. It has inertia. It lags behind for just a fraction of a second. This creates a temporary lean condition, what we call a flat spot or a hesitation in the engine, and it happens precisely when you're demanding more power. Not good. So here's the solution, and it's a very direct mechanical one: the accelerator pump. It's just a little pump or a piston that's physically linked to the throttle. When the pilot pushes the throttle forward quickly, this pump mechanically injects a measured squirt of raw fuel straight into the venturi. This extra shot of fuel covers for the fuel's inertia, smoothing out that momentary lean condition and giving you a smooth, positive engine response. Now, at very high power settings, we need a mixture that's actually richer than what's chemically perfect, what we call stoichiometric. Why? Well, that extra fuel doesn't all burn. It actually acts as a coolant inside the cylinder, pulling heat away to prevent overheating and detonation. The power enrichment jet, or sometimes called an economizer, is an extra jet that only opens up at high throttle settings to provide this critical extra flow of fuel. Okay, we've done it. We've built the complete system from the ground up. We understand the why behind every single component. So now, it's your turn. You're in the interview. The examiner leans forward. Let's frame the perfect answer. First, you'll get the big conceptual question. Tell me about, or walk me through. What they're looking for here is to see if you can connect all these different subsystems into one coherent story. They're testing your ability to explain a complex system logically and clearly. Next up, they'll hit you with a specific scenario. This is a test of your practical knowledge. Can you diagnose a problem and pinpoint the exact component responsible? This shows a much deeper, more operational level of understanding. So this, right here, is your framework for a captain-level answer. Number 1, always start with the core principles. Talk about the YouTube and the Venturi effect. 2, use precise professional terminology. Say pressure differential, don't say suction. Say stoichiometric, not the perfect mix. 3, for every single component, explain the why before you explain the how. State the problem it solves first, then describe the mechanism. 4, link the systems to phases of flight. Talk about the idle jet for taxi, the accelerator pump for the takeoff roll, the enrichment jet for the climb. And finally, and this is the mark of a true professional, show your airmanship. Conclude by mentioning the system's inherent limitations, specifically its susceptibility to carburetor icing. That is the answer that gets you the job. That is the captain's answer.